Solid-state batteries get all the attention because they promise better performance. But here's the number that actually matters. Over 70% of EV buyers still cite price as the main reason they don't switch, not charging speed or battery life. Right now, solid-state doesn't meaningfully lower vehicle cost. Sodium-ion does. Analysts estimate sodium-ion cells can be 20 to 30% cheaper than lithium-based batteries, with more stable raw material pricing. At the vehicle level, that's the difference between an EV staying above $30,000 or finally dropping below it. So the real question isn't which battery is better. It's which battery reaches scale first and changes buying decisions sooner. If solid-state is the long-term future, why are automakers investing in cheaper chemistries today? What problem does sodium-ion solve that solid-state doesn't, especially for Tesla's next mass-market vehicles? And why might a worse battery reshape the market before a better one ever shows up? This is autogearshift. We focus on what moves markets, not what looks good on spec sheets. Let's break it down. What solid-state actually fixes? Solid-state batteries are built to fix engineering limits, not pricing limits, and the numbers make that clear. From a technical standpoint, solid-state solves real problems. Removing liquid electrolytes reduces fire risk and allows higher charge rates without aggressive cooling. That's why many solid-state programs target 3 to 5 times faster charging and operating ranges from -30 degrees Celsius to 80 to 100 degrees Celsius, compared to conventional lithium-ion packs that start losing performance below freezing and require thermal throttling above approximately 60 degrees Celsius. Cycle life is another area where the gap looks massive on paper. Most automotive lithium-ion packs today are engineered for roughly 3,000 to 5,000 full cycles, translating to about 300,000 to 500,000 miles in real-world use. Solid-state claims often project 20,000 plus cycles, and in extreme cases far more, far beyond the usable life of the vehicle itself. But here's where the market reality breaks the story. In 2025, battery packs still make up roughly 30 to 40% of the total cost of a mass-market EV. For a $35,000 vehicle, that's about $10,000 to $14,000 just for the battery. Early solid-state manufacturing is expected to push cost per kilowatt-hour higher, not lower, due to lower yields, new equipment, and stricter quality control. Even optimistic projections place early solid-state cells 20 to 50% more expensive per kilowatt-hour than mature lithium-ion lines. That means a solid-state upgrade doesn't reduce the sticker price, it increases it. And that's why solid-state doesn't change buyer behavior today. A 5-minute charge sounds revolutionary, but for most drivers charging at home overnight, the difference between 25 minutes and 10 minutes on road trips doesn't justify a $3,000 to $5,000 higher vehicle price. Solid-state makes EVs better machines. It does not make them easier to buy. So let me ask you, if you were shopping for an EV today, what would actually change your decision? Comment 1 if better battery tech would convince you, even at a higher price. Comment 2 if a lower price matters more than specs. Tell us why in the comments. If you've made it this far, that probably means this kind of analysis actually works for you. So don't disappear after this video. Hit subscribe and turn on notifications so you keep getting breakdowns like this. The kind that question hype, timing, and real-world risk. We're closing in on 23,456 subscribers, and if you're still watching, you might as well be part of the group that cares about what really moves the market. Now, let's continue. Why affordability is the real battlefield. When people hear solid state, they instinctively think next-generation EVs, longer range, faster charging, fewer compromises. But once you put real 2025 sodium-ion data next to those claims, something interesting happens. Sodium doesn't try to win on range. It wins on system economics and reliability. Let's start with the numbers that actually exist today, not 2030 slides. In 2025, Second-generation sodium-ion cells from large manufacturers like CATL are reaching 160 to 175 watt-hours per kilogram at the cell level. That's still below high-end lithium-ion, but it's no longer a toy number. In practical terms, that translates to 350 to 450 kilometers real-world range in a compact EV, enough for daily commuting, urban fleets, delivery vans, and secondary household cars. Now compare that to solid-state batteries like Donut Labs claims. On paper, 400 watt-hours per kilogram sounds revolutionary, but higher energy density creates secondary costs. Stronger cooling requirements, tighter charging control, higher failure consequences, stricter manufacturing tolerances. Sodium-ion goes in the opposite direction. Because sodium chemistry is far more thermally stable, manufacturers can design simpler battery packs. Less cooling mass, less safety buffering, less software overhead. In 2025 estimates, sodium-ion packs are projected to cost $60 to $80 per kilowatt-hour, roughly 30 to 40% cheaper than lithium-based alternatives at the pack level, not cell level. That matters more than range for most buyers. Think about how cars are actually used. The average driver doesn't exploit 600 kilometers range. They exploit predictability, predictable winter behavior, predictable charging time, predictable degradation. This is where sodium-ion quietly outperforms expectations. In cold climates, sodium-ion batteries retain significantly higher usable capacity at sub-zero temperatures compared to lithium-ion. Real-world testing shows less voltage collapse at minus 20 degrees Celsius, which means fewer range surprises in winter. Something solid-state still hasn't proven at scale. Charging is another misunderstood area. Sodium-ion batteries in 2025 can already handle 15 to 20-minute fast charging, 0 to 80%, without aggressive thermal throttling. That's not 5 minutes, but it's repeatable, day after day without pushing the cell into edge case stress zones. Solid-state fast charge demos, by contrast, often rely on controlled lab conditions, lower C-rate repetition, or undefined degradation trade-offs. 5 minutes sounds great once. Fleet operators care about what works 10,000 times, not once for a press release. Cycle life reinforces this gap. Sodium-ion batteries are targeting 3,000 to 6,000 full cycles in real-world duty. That's enough for 10 to 15 years of daily driving, even with frequent fast charging. And because sodium doesn't depend on lithium, cobalt, or nickel, supply volatility risk is dramatically lower. Solid-state batteries promise tens of thousands of cycles, but that advantage only matters if the battery is being deeply cycled, something private passenger vehicles rarely do. This is why sodium-ion adoption in 2025 is accelerating not in luxury EVs, but in entry-level city cars, ride-hailing fleets, delivery vehicles, grid-linked mobility systems. In these use cases, cost per kilometer matters more than peak energy density. So here's the uncomfortable truth solid-state marketing avoids. A battery doesn't need to be revolutionary to reshape the EV market. It needs to be cheap, boring, and predictable at scale. And in 2025, sodium-ion checks more of those boxes than solid-state does. Why sodium-ion moves EV markets faster than solid-state ever could? From 2025 onward, the EV market is no longer constrained by whether batteries can deliver more range. It is constrained by whether manufacturers can ship acceptable EVs at prices normal buyers will actually pay. That change in constraint is exactly why sodium-ion moves faster than solid-state. By late 2025, global sodium-ion production capacity is projected to exceed 100 gigawatt-hours annually, driven primarily by CATL and several Chinese Tier 1 battery suppliers. These are not pilot lines or demonstration plants, but industrial-scale facilities designed for continuous output. In contrast, solid-state battery capacity over the same period is expected to remain below 5 gigawatt-hours worldwide, with most output coming from semi-commercial or validation stage production. This gap matters because battery cost does not decline when chemistry improves on paper. Cost declines when factories run stably. Sodium-ion cells are inherently more tolerant to manufacturing variability. They require less aggressive moisture control, simpler electrode materials, and more forgiving formation processes. As a result, early sodium-ion production lines are achieving first-pass yields that are estimated to be 10 to 15 percentage points higher than those seen in next-generation lithium or solid-state lines at comparable maturity. Higher yield is not a technical footnote. It directly determines whether a battery program survives contact with financial reality. Now place that manufacturing advantage into the context of vehicle pricing. Between 2025 and 2027, the fastest-growing segment of global EV demand sits below the $25,000 price threshold. At that level, buyers are not cross-shopping kilowatt-hours. They are deciding whether an EV is affordable at all. In this segment, a reduction of $2,000 to $3,000 in battery cost can determine whether a vehicle reaches mass adoption or remains a compliance product. This is where sodium-ion quietly reshapes EV strategy. With projected pack-level costs in the $60 to $70 per kilowatt-hour range, sodium-ion allows automakers to either lower vehicle prices directly or protect margins while absorbing rising costs elsewhere in the vehicle, such as safety systems, software, or regulatory compliance. Solid-state batteries move economics in the opposite direction. Even optimistic forecasts place early solid-state packs above $120 per kilowatt-hour well into the late 2000s, which confines them to premium or experimental vehicles with limited volume relevance. This distinction becomes especially important when we look at Tesla. Tesla has never won by adopting the most advanced battery first. It has won by deploying batteries at scale, with predictable cost and stable supply. Historically, Tesla only integrates new battery technologies once they improve cost per vehicle, reduce manufacturing risk, and strengthen supply chain control simultaneously. Solid-state batteries currently fail all three conditions. Sodium-ion aligns with them. A sodium-ion pack in the 45 to 55 kilowatt-hour range can deliver roughly 350 to 400 kilometers of real-world range, which is more than sufficient for urban commuters, second-car households, rideshare fleets, and autonomous mobility platforms. For a future Model 2 class vehicle, that trade-off makes strategic sense. It allows Tesla to reserve high-energy lithium packs for long-range and performance variants, while deploying cheaper, more abundant chemistry, where energy density simply does not matter as much. There is also a geopolitical layer that cannot be ignored. Sodium-ion batteries rely on widely available materials that are far less exposed to lithium mining bottlenecks and price volatility. For a manufacturer operating at multi-million vehicle scale, supply predictability often outweighs marginal gains in energy density. A battery that ships reliably every quarter beats a better battery that ships inconsistently. This is why sodium-ion does not need to outperform solid-state to win relevance in EVs. It only needs to arrive at the right moment. And that moment is now, while the market is still fighting price ceilings rather than range anxiety. Solid-state batteries may eventually dominate niches that demand extreme endurance or energy density. But EVs are no longer niche products. They are mass-produced transportation tools governed by cost curves and factory throughput. And in that environment, sodium-ion does not just compete with solid-state. It shortens the window in which solid-state makes sense for mainstream EVs at all. Here's what really matters if you're thinking like a buyer, not a spec watcher. Every time a next-gen battery appears, early adopters take the risk, not the automaker. And when that technology turns out to behave differently in the real world, it's owners who pay through depreciation, range redefinitions, or resale shock. Sodium-ion reduces that risk by being boring, cheap, and predictable. Solid-state increases it by being new, fast-moving, and still undefined at scale. And that leads to the next problem no one wants to ask yet. If Donut Lab's battery charges in minutes and survives extreme abuse, is it really a traditional solid-state battery? Or is it starting to behave like a supercapacitor with an energy disguise? That's the real test facing Donut Lab's tech, and that's exactly what we'll break down in the next video: solid-state or supercapacitor. The real test facing Donut Lab's battery. Stay with autogearshift.